So welcome to everyone, and welcome to Mike. Thank you very much, Mike, for having preparing these lectures.
Thank you for the invitation. All right, thank you very much. So this is the second talk, so there was a reminder of where we were. So last time I described the basic syntax of this theory that we're proposing, called Higher Observational Type Theory. HoTT, which is either fortunate or unfortunate abbreviation, depending on your point of view. And so today, my goal is to convince you by syntactic and semantic means that we need to augment this syntax with a notion of symmetry. And we'll start talking about the semantics as part of that. And then next time we'll get to univalent universes. So, but before we dive into talking about symmetry, I want to do a little bit of review of where we got to last time, because it was a week ago, and maybe we have some new people. Maybe not everybody went back and rewatched the video yesterday. And in the process of reviewing, I want to also reformulate the theory a little bit, because partly because some of the questions that were asked afterwards, I think can be nicely answered by this reformulation. And some people may prefer a different way of thinking about things. So last week, I described what I might call sort of the book version of this theory. In other words, it's sort of the version that you would write sort of as an introductory or textbook presentation, where you sort of start with simple things, and then you notice that this simple thing has to be generalized to a slightly more complex thing, and then you go on and on and on, step by step. But maybe this is not sort of the cleanest way to present the whole theory as a completed whole. And so sort of once we've got the whole theory, then we can sort of reformulate it in a way which is a little bit more concise and clean as a unit. And a particularly useful way to do that is to pay attention to what happened when we ended up with not just the ordinary app and id and identity types. Right, we started out with this sort of simple notion of app, where we just bind one variable, but then we eventually decided that we needed a more general version of app that can bind multiple variables at once. And in that case, the term that those variables are bound in exists in the ambient context gamma, extended by some additional list of variables. So you might call it a context suffix. And a context suffix like that is sometimes called a telescope. And it turns out to be helpful to think about these as being reified in some way into, you might call it, telescope calculus. So let me present the whole theory right now, sort of review very quickly going through it in the language of a telescope calculus. So we have some kind of a judgment for what it means to be a telescope, and the telescopes are defined inductively as lists of types in the ambient context. So we have an empty telescope, epsilon, and then if I have a telescope and I have a type in the context extended by that telescope, then I can add that type to that telescope and get a longer telescope. And just like a closed context, a telescope has elements which you can call substitutions or tuples or lists. So the empty context, the empty telescope has an empty list, a single element. And then if you extend a telescope by a type A, then you can extend an element of it, right? If you have an element of delta, I can extend it by an element of A. But since A exists in the context delta, then a little a has to be in the context A substituted by my little delta, so that it is sort of in the same context as little delta. And so then you have this notion of substitution of an element of a telescope into a type or into a term, which is defined in the usual substitution way by induction over types and terms. Just maybe to emphasize here that we're generally going to be omitting these ambient contexts gamma, and I'm doing that sort of everywhere here. But I included it up here so that we could make clear that what's going on is we're extending the ambient context by a telescope when the telescope appears in to the left of the turnstile like this. So once we have this notion of telescope, then we can define identity telescopes, which are sort of lists of identifications, which are sort of the natural thing on which the in-array identity types and app depends. So we have the identity telescope of a telescope. So if I have a telescope and I have two elements of that telescope, then I can talk about the telescope of identities between them, which is supposed to be just a pointwise list. So we have inductively, we can define that by saying that we have, if we have an identification between two elements of delta over here, and then an identification between the two elements of the two things that those elements are extended by to make these additional tuples here. And this identification here has to depend on the ones that we previously had, because all the types in the telescope depend on the previous ones. Then that dependent identity type is now sort of what it depends on is an element of this identity telescope. So for any type here that depends on a telescope, and any elements of that type that lie over two elements of the dependency, the telescope identification, we get a dependent or heterogeneous identity type. So you sort of think about delta as living down here, and then upstairs above it we have A, and then we have an identification between a delta and delta prime, which is this thing I'm calling rho. And then if we have an A and an A prime that live in the fibers over delta and delta prime, then we can talk about the type of identifications living over rho. And that's this dependent or heterogeneous identity type. And in the case of dependency on the trivial, the empty telescope, we get this sort of non-dependent identity type. So last time I defined the dependent or heterogeneous identity type in terms of app into the universe. And that's sort of the nice way to motivate it, I think. But if we're defining the whole theory all at once, maybe it might be more convenient to postulate it separately and then make them coincide later. You can choose to do it either way, but today I'm doing it this way because some people might want to see it this way. So we talked about how these identity types compute on all the type formers. So an identity between pairs is a pair of identities. An identification of functions is where we have this sort of fattened up version of function extensionality that says to identify two functions f and g, we show that any identification in the domain maps to an identification in the codomain between f of the left hand and g of the right hand. And now that we have these general dependent or heterogeneous identity types, we assert these same computation rules for those. And we also have similar rules for the dependent versions, the sigmas and the pi types. I mentioned, write those down briefly last time. The basic idea is they're exactly the same as these non-dependent versions, except now on the last identities here, identification types here, we end up with an extra thing added to the telescope, because here B depends on A, and so the identification in B has to depend not just on delta but also on A, and so we have to add this identification here to the telescope identification that we're depending on. We also have that all these dependent identity types are what we call one-to-one correspondences. And again, last time we derived that from app into the universe, but we can also just assert it directly as sort of a primitive operation. So one-to-one correspondence means that if I have something fixed on one side, say on the left, then the type of things on the right that corresponds to it, that are identified with it over some fixed row, is contractible, and similarly on the other side. So we have these basic things. I didn't use this notation last time, but whatever they are, there's some witnesses of contractibility here. And we talked about how in particular, the centers of contraction of these types here constitute transport. So in particular, there's given a little a over here, there's an element of this type here. So that consists of an element of a over the other side, which we call transport of little a over across the identification row. And we also have an identification of a with its transport. Oh, sorry, this a prime here should be transport. Right, so A is identified with its transport over row. And these witnesses here also compute on all type formers. So in particular, that means transport in a pair type is a pair of transports, and so on and so forth. I'm not going to write out all the rules for that. We also have this general higher dimensional explicit substitution, or app, which says that every term respects all identifications. So if I have any term t depending on any telescope delta and some identification in delta, then I can bind delta in t and apply it to that identification to get an identification between the outputs of t substituted by the left and right endpoints of that. Some people in the Zulip discussion afterwards were asking about whether this really has to be an explicit substitution. And you can imagine making this implicit as well, like ordinary substitution, so that instead of app being part of the syntax, it's actually an operation on syntax. Instead of, and you should be able to do it that way as well, but I sort of like to think of it like this because it's sort of more complicated than ordinary substitution, and I like to be able to just write it down. But I think you could probably do it either way. There's sort of one exception to the claim that this computes on all terms, and I'll get back to that in a couple of slides. but it computes on nearly all terms, right? So any particular term we've got, a pair, a projection, an application, an abstraction, and so on, this computes on everything. And this is sort of like the behavior ordinary substitution. It's not like an eliminator that computes only on introduction forms. The substitution actually sort of pushes inductively through all possible terms that you could write down, even neutral or redexes. And the particular case of app, when the telescope is the empty telescope, I guess this should be epsilon really here. When we have the empty telescope, then that reduces to what we call reflexivity. That's basically the definition of reflexivity, is the zero array version of app. And then finally, we have univalence. So remember, we'd like to define univalence, the identifications in the universe. We'd like to sort of define them to be these one-to-one correspondences with this sort of relational notion of equivalence, a correspondence here, a type dependent on a family of types dependent on both sides, which is contractible pointwise on either side. But instead of actually defining it to literally equal that, we give it, we make it an extract. We make the correspondence as a retract of the identity type. And so we have this thing here, which I was calling promote, and this thing, which is sort of demote, which takes an identification back to just a one-to-one correspondence. And we have a beta law like this, but we don't have an eta law. And I'll explain, we won't get to explaining why this is today, but we'll get to that next week. And once we have this, then we can identify this dependent identity type and these witnesses that it's a one-to-one correspondence with the ones that we would get from taking this type family here, B, and regarding it as a map into the universe, so that I can do app of it and then demote it to a one-to-one correspondence and extract the pieces of a one-to-one correspondence. The correspondence gives me the identity type, and then these two witnesses of contractibility give me these correspondence witnesses. So again, last time we essentially defined the left-hand sides here to be the right-hand sides, but if we separate them, maybe it feels a little bit more natural if our universes are Tarski style, and allows us to talk about types that don't lie in any universe at all, if we wanted to do that. So the last thing that I wanted to mention as part of this sort of review is to explain that asterisk on the claim that app computes on everything. So there's one exception that app doesn't compute on, which is that we have reflexivity of a variable. And this is sort of a neutral form, so in particular a normal form. And so I gave rules last time for computing app on variables. But what happens if you try to compute refl on a variable? So refl is the zero array version of app. So we have app with an empty telescope on a variable. And so we're in the case when the variable doesn't appear in the telescope. And the rule was that in that case, app computes to refl. And so in this case, you're just saying refl computes to refl, and that doesn't give you anything useful. So refl is essentially a neutral form. It doesn't compute until you substitute something that's not a variable for y. And this includes as examples of sort of other terms that you sort of have to be neutral in some way. Like if you do app of a variable function, then that turns out to compute to refl of that function applied to something, and then you can't compute any further because you've got refl of the function. Or if you have an identity type of a variable type, there's nothing you can compute that to, so it computes to refl of that type as long as the type is in the universe, and that it doesn't go any further than that. And then you also get the refl of refl and refl and so on, which are also neutral. Okay. So that's my review of the theory that we had last time, expressed in terms of expressed in terms of these telescope calculus. Maybe I should say explicitly, so if you have questions during the chat, please do chat them to Steve, and then he can ask me. So I don't want anybody to sort of get stuck on a little bitty thing and then get lost for the whole rest of the talk. But it sounds like we don't have any questions right now, so I will move on. So I said I want to convince you that we need this sort of symmetry operation. And so let's talk about the problems that explain why we need it, at least in the syntax for now. And these problems arise by considering a cubical structure that arises from our identity types. So I don't think it's appropriate to call this theory a cubical type theory, because it doesn't have dimension variables, it doesn't have explicit cubes in the syntax in any way, but it has an emergent notion of cube, which is the same as any other type theory that has dependent identity types, which includes actually Book HoTT. And the way this notion of cube arises is by considering id at an id type. Right? So look at this thing that I've written over here. So what does this mean? So I've got I'm depending on 2 copies of A as sort of my downstairs thing, and then above that, the thing that's depending on it is id A. So maybe over here I have a pair. Maybe I'll call this A00 and A10, and then over here I have another pair of elements of A, maybe A01 and A11, and then over each of those pairs I have an identification between them. So I'm going to call this A20, and that is essentially that's a path or an identification between these two, and so you can sort of write it, consider it, kind of draw it like this between these 2 points. And then here I have another one, A21, which is now an identification between these 2 points over here. And now to identify this A20 with A21, I have to have a heterogeneous identity type over an identification downstairs between these pairs. But an identification of pairs is just a pair of identifications. So now this is a pair of an A02, which identifies A00 with A01, and an A12, which identifies A10 with A11. And so once that's the things that appear up here. And so now once I've given all that data, I can ask about what it means to identify A20 with A21 over these other 2. So these other 2 here you can regard as filling in the boundary here of a square. And then A22, the inhabitant of this dependent identity type, lives inside this square. So the roles of these, the left-hand boundaries and the right-hand boundaries are asymmetrical. And that's essentially sort of the reason why we eventually end up needing some kind of symmetry. But we do have this sort of intrinsic notion of square, which we get from having heterogeneous identity types. And if we consider id, we get a notion of 3-dimensional cube, and id, and so on and so forth. So we actually get all these higher dimensional cubes automatically. Now, if you're a homotopy theorist, or if you're used to cubical type theory, you might ask, well, what can we do with these cubes? So the things that we would like to be able to do with cubes, for instance, we'd like to be able to fill cubical horns. And we can do that in some cases. So remember that you said dependent identity types are one-to-one correspondences, and so we have transport. And so in particular, that means if I have an A20, and I have these things that it might depend on, then I can transport it across to get an A21. And sort of geometrically, that means that I have this piece here, which is a cubical horn that's missing the right-hand path and the inside. Then I have transport that moves this thing on the left over to the right, and then I have lift, which essentially fills the square. So this gives me a left to right cubical horn filler, and the transport from right to left gives me right to left cubical horn filler. And I have similar things in higher dimensions, but they only go from left to right. At the moment, it seems like we don't have any way to fill horns from top to bottom or bottom to top. You could, if you're a homotopy theorist, you might regard this as a problem. If you're a cubical type theorist, you might expect that this is going to give rise to other problems. But it may be intrinsically, it's not obvious that this is something that we necessarily need. So let's maybe go on and see some more serious problems that we get here. So another thing we can do with cubes is we can ask for degenerate cubes or squares, which are sort of reflexivity or identities in one direction. And in dimension 2, we have these reflexivities, these degenerate squares in both dimensions. So on the one hand, if I have a single identification in A, then I can consider reflexivity of that, and that's a homogeneous identification. But our functoriality rules say that's the same as a heterogeneous identification over reflexivity. And so that refl of A2 looks like this sort of degenerate square, which is sort of constant going from left to right. On the other hand, I can consider refl as an operation that takes a point to an identification. And then I can consider that, and I can app that on A2. And so that if A2 identifies A0 with A1, then app refl of A2 identifies refl A0 with refl A1. And so the things that are being identified by a square are the left and the right boundaries. And so this gives me one of these degenerate squares, which is constant in the up-down direction. So we do have these two degenerate squares, but they don't behave quite like we might expect. So for instance, if A2 is actually itself reflexivity, then you might expect that these two different doubly degenerate squares are in fact the same, that they should be sort of constant and there's only one thing, one sort of constant square, but the rules that we have so far don't actually relate these things to each other in any way. It's not clear how they're related. So that may be another problem. Maybe it's a problem, maybe it's not a problem. Here's something that's definitely a problem. This degenerate square on one side is a stuck term. We can't compute with it because I told you that refl on a variable doesn't compute. And now here in the subscript, we have refl on a variable, but I can't do anything else with it because that variable is immediately bound. And I don't have any rule for computing app on a refl. What I'd like to say is that should compute based on the structure of A2, just like refl A2 does, like the other degenerate one does. But our rules for app don't inspect the identification argument. App only computes based on its subscript, its bound term. Right? So with the rules we've given so far, this is a stuck term. Now, you might say, again, do we care? Is this weird sort of cube? Maybe it's okay that it's stuck. Do we really need to be able to compute with it? And the answer is yes, we really do, because this actually breaks canonicity for even the natural numbers. Just having this sort of stuck thing. So there's an intuitive homotopy theoretic reason. So if you're a homotopy theorist, then you can think, if I do this thing to reflexivity, then I get this sort of square that has constant boundaries, but I don't know that it's a constant square. And a square with constant boundaries is essentially a self-homotopy of the identity equivalence of a type. So it's like the homotopy from the identity, the constant homotopy, or a map from that type to itself. And a self-homotopy of the identity is essentially an element of this thing, which is sometimes called the center of an infinity groupoid, which picks out a loop at every point. And so in particular, if I take A to be this type to be something like the circle, then I get a loop at base, which is stuck because it came from this stuck term, and the loops at base in the circle are integers, and so I have a stuck integer. And you can also give an explicit argument using two universes that doesn't require having a circle. So however you do it, we sort of have a problem. We need to be able to compute with this thing. So we have all these problems that come from cubes and sort of squares, and we'd like to solve the problems in some way. And it turns out the natural way to solve them, we think, is to introduce this operation of symmetry that sort of allows us to get around the fact that the left sides of a square and the top and bottom of a square play very different roles by switching those roles. So we introduce a symmetry operation which transposes a square. So here I've in red on the right-hand side of here, I put these things that change. The left hand, the lower left and the upper right points don't change, but the other 2 points swap with each other, and these other two sides of these two sides of the square swap with each other in pairs. And then sim of A22 sort of takes this square with this boundary and produces a square with this boundary. So this is what the rule looks like. You can see it's taking these two type terms and putting them over here, and these two terms and putting them up here, changing which is the dependency and which are the endpoints of the path, equal the identification. So that's the symmetry operation, and so that actually solves all the problems that we have if we do it carefully enough. So if we want to fill from bottom to top, for instance, I can take a horn like this and transpose the horn, and then fill from left to right, and then transpose that square back again. So that's fairly straightforward. It gives us a way to fill from bottom to top and top to bottom, and similarly in higher dimensions. If we want to deal with the problem of stuck terms, which was the third problem here, then the natural thing to do is to say that this this thing here, app refl of something. Remember, what was app refl of something? Remember, app refl of something was a square that's constant in the up-down direction. So the natural thing to compute it to is the symmetry of the other degenerate square, which the refl of A2, which was constant in the left-right direction. So I can take symmetry of this, and it gives me something that looks like this, and I'll just say that's how I define this thing on the left. And the nice thing about that is that doing this has taken A2, which is sort of the non-trivial term, the potentially non-trivial term in here, and moved it from the argument of app down into the subscript of refl. And now refl computes on its subscript, and so the computation can proceed, as long as the symmetry piece can also then compute on the result of refl. Right? So we have to give rules for computing symmetry. And for the most part, this is fairly straightforward. So here's an example. Suppose I want to compute symmetry on a product type. So what is a square in a product type? Right? This here is the type of squares in a product type. Down here in the subscript, I have id of A cross B. that by definition is a product of ids, id A cross id B. And now I have id of a product, but this id here is id of a product. So now I can use this computation rule again, and I get id A and id B. And here I've did some sort of munging of the dependencies so that I can see that it's really literally just a square in A and a square in B. And so I can just do symmetry in A cross B is just a pair of symmetry in A and symmetry in B. So in the most part, this is computing symmetry is pretty straightforward. If I want to generalize this from non-dependent product types to sigma types, then we need some notion of dependent symmetry. And the notation here gets a little bit hairy, so please don't spend too long making your eyes glaze over here. But the basic idea is that we have some type A that depends on some telescope delta, and then we have sort of a square in delta, right, here, which then we have a square in A that depends on. And then what happens is I can do the symmetry of this square relative to that square, and I get a square in delta, a square in A, which now depends on the symmetrized version of the original square in delta. And so I sort of symmetrize in A, and I have to symmetrize in the things it depends on at the same time. And then I can do symmetry in a sigma type by doing just again symmetry in a pair, but now this over here on the right, I have to add this thing here to the dependencies of my square on the right. For symmetry in functions, let's think about what a square in a function type is. Again, so don't the notation gets a little bit hairy, but the basic idea is actually not too complicated. So here we have id of a function type down in the subscript. Id of a function type is functions that take any identification in A to an identification in B. So I'm using our fattened up notion of function extensionality in the subscript here. And now I've got id of a pi type. It's actually a triple pi type. And id of a pi type, again, we have this fattened up notion of function extensionality. So each of these pi's here gets expanded out into a triple pi when I compute id on it. So that one gives me this one, that one gives me this one, and that one gives me this one. And if you look at exactly what this sort of 9 pi's look like, it's actually describing exactly a square in A, right? So I've got 4 points in A, and then I have 4 identifications in A, and then I have a square that sort of fits in them. And then the output here is going to be id of this thing here, which is just a square in B. So a square in a function type is a function from squares to squares. It basically says, given any square in A, then I know what to do to its boundary to give me a square in B. And then the particular square in the function type says, given what happens on the boundary, I tell you how to map this square to that square. And so if we want to compute symmetry on it, what we do is we just conjugate this operation by symmetry on a square. First, we do a symmetry in A, then we apply the function on squares that we had before, and then we do a symmetry in B to the result. Again, don't worry too much about the details, but right, you can do pi types and dependent symmetries and so on in a similar way. The basic idea is right, you have symmetries in A and B, and you put them together to get a symmetry for other things like A cross B and A cross B and so on. So that gives us a way to compute with symmetry, and that sort of solves this problem of being able to compute with AppRefl.
Mike, there's a question about the symmetries from Jason Gross.
Yes.
Can you give some intuition for why we need to add symmetry separately? For example, does it correspond to some homotopical object that's independent of the other type formers? That's the question.
Let's see. Well, the short answer is that we need to add it because we don't have it, I guess. Why homotopically, maybe from a homotopical perspective, maybe that will make a little bit more sense when I start talking about semantics later. If you, so for instance, this horn filling issue, right? So in a cubical set, we expect to be able to fill horns in all directions. but the syntax that we've got so far only tells us how to fill horns in one direction. And so this extra symmetry operation is a way to say, given this way of filling horns in one direction, that can also necessarily then also fill horns in a different direction.
Okay.
Yeah, I'm not sure if I have more to say about that at the moment. Maybe afterwards we can talk more about exactly what would be a good answer.
Okay.
That might require some back and forth.
Here's another question, as long as you're answering questions. Valerie Isev asks, does this mean we don't have J without sim? Question mark.
That's a good question. That's a good question. Yeah. That came up on the Zulip chat after last week as well. I'm not going to go out a limb on. I'm not going to go on a limb and say we don't have J without sim, but I believe that the proof I have, not of the existence of J, but of the computation rule for J, I believe the proof I have of that does depend on having these top to bottom fillers, and which we get from sim. It's possible there might be some way to get it without that.
Okay, here's another one that is suggested for the end, but I'm going to ask it now anyway, because I don't want to forget. It's, how does sim compute on sim?
That's my next slide.
Now.
Yes, thank you. So we also want some sort of rules for the way symmetry behaves in addition to how it computes on particular examples. And one of those should be that it's an involution. So if I take a square and I transpose it and then I transpose it back, I should get the original square. And it should also be functorial. So if I have a function f from a to b, and I take a square in a and I transpose it and then map it into b, I should be the same thing as mapping it into b first and then transposing it. Now these rules have a bit of a funny status. They're I mean, this one kind of looks like a computation rule, and you might be able to implement it that way. This one, it's not clear exactly how to direct it. And so I think our current plan for implementing rules like this is to implement some additional sort of equality munging on terms that are already neutral. And there's some ways of doing that have been studied in other contexts. So we don't expect that this will be a big problem once we sort of have everything written down. So one reason that we want this second rule here is not just because it's sort of sensible, but also because it solves the second problem that I mentioned of the two doubly degenerate squares. So if I instantiate this at the zero array app, then sort of this thing over here completely disappears, and I just have REFL of REFL. And then over here, what happens is this thing disappears, and I have REFL of REFL, and I'm doing symmetry on REFL of REFL. So the symmetry on REFL of REFL is also equal to the other app REFL of REFL, because that's how we define this thing over here to compute. It computes to that. And so this equation here tells us that these two doubly degenerate squares are in fact equal to each other. So that's great. There's one more rule for symmetry, which again, we're going to have to implement in this sort of munging neutral terms way in general, which has to do with higher dimensions. So now if you think about an n-dimensional cube, which again means an iterated id, and so on, then what we would expect is that we can permute all n dimensions of a cube like that. So any sort of permutation of the n dimensions should be an action of that cube. That would be sort of the consistent way to think about higher dimensions. What we have, which sort of arises naturally from what we've given so far, right? So we've only given a symmetry operation on squares. And what that gives us when we look at it acting on an n-dimensional cube is it gives us a way to transpose adjacent dimensions. And I think you can see this if you think about three-dimensional cubes, right? So a three-dimensional cube is something in id. And so if I do sim of id, then what that does is it acts on these two ids, and it transposes those ids into the output and gives me, it transposes those dimensions and leaves the third dimension the same. On the other hand, what I can do is app of sim, And then what that is sort of acting on these two ids here. And then this other id is sort of what the app is promoting that to act from this id to the other big id, and it transposes these two second dimensions on down there. And the same thing is true in higher dimensions. If you sort of have a chain of apps and then a sim and then a chain of ids below that, that gives you a way to transpose two adjacent dimensions in an n-dimensional cube. But fortunately, transposing adjacent dimensions is enough to be able to permute arbitrary dimensions, because the symmetric group on n things is generated by adjacent transpositions. So this is a sort of a standard presentation of the symmetric group in terms of these adjacent transposition operations, sigma 1 to sigma n minus 1. And you have a bunch of relations here that you have to use to present the symmetric group. And two of these relations we already have. So this one here says that each of them is in involution. We already have that here. All of the symmetries are in involution. And this second one here says that if I transpose two things over here and then two things over here that aren't related to each other, then I can sort of shuffle those things up and down and commute them with each other. And that follows from sim commuting with double app, because remember, when I take, if I sort of have a tower of ids, then symmetry in one dimension is going to be apps and then a sim here, and the other symmetry in lower dimensions is going to be a bunch of more apps and then an id. And so these apps up here below, above this symmetry, are going to be app that's going to commute with this symmetry according to that rule. So that gives us the second relation. And then, but we want this third thing, which is sometimes called the braid relation. And so we get that from asserting a rule that looks like this. So again, don't worry too much about what this exactly means. I've omitted a lot of annotations to make it more readable. But again, we sort of implement this by sort of munging the neutral terms. So that is all I wanted to say right now about symmetry syntactically. So at this point, we're going to switch gears a little bit and start talking about semantics. But it's sort of not completely unrelated, of course, because we've explained how to compute with this particular stuck term. But of course, we don't know that there might not be other stuck terms that we haven't found until we actually prove a canonicity or normalization theorem. We haven't done that yet, but sort of, I guess, from a categorical or modern perspective, maybe the way to approach to a theorems like this is with some kind of a gluing argument. What we need in order to do a gluing is we need some kind of semantics based on sort of sets, or in our case, it's going to be some kind of cubical sets. And so moving to semantics at this point is a natural thing to do. So let's think about exactly what categorical structure corresponds to the identity types that we've got. So when we model our type theory in some kind of a category, then the objects of that category act like contexts in the syntax, roughly speaking, right? And then the types in some context are the objects of some slice category or vibrations or something like that over a particular context. And so the operation on contexts that comes from our identity types is this operation here, which I'm writing capital id. So we've got these identity telescopes or identity contexts, but they depend on two elements of that same context. So it takes a context delta and spits out, if I want it to be a closed context, then I've got to have two copies of delta first, followed by its identity context. And as a sort of sitting on its own as an object of this category, this acts like what a homotopy theorist will call a path object, as something sitting inside the diagonal of delta. Right? So there's a REFL operation which maps delta to this thing, which sets little delta prime to be the same and rho to be reflexivity. And then on the other hand, I can project out the two copies of delta here, and that just gives me categorically as the product delta cross delta, and this whole thing here is the diagonal map. So we have a functor, right? So app makes it into a functor. So we have a functor from our category C to itself, the capital ID, and then it has this path object structure, and it also has these symmetries, which sort of commute id with itself applied twice, and we sort of have this symmetry action on n-fold identity context that arises from that. So if we encapsulate that in categorical language, what that means is we have this functor here, and then we have natural transformations from the identity functor to id. So that gives us this reflexivity term here, which is natural in this functorial structure. And then we have these two projections from id back to the identity functor, which gives us these map to delta cross delta. And these two composites are both the identity. So that gives us a relation between these natural transformations. And then we have these symmetries, which are natural isomorphisms from this square of this functor to itself, and they have to satisfy the symmetry relations. And a nice way to encapsulate this structure is by saying there's a particular monoidal category, a small little monoidal category that's generated by this sort of structure, which acts on our category C. So I'm going to call this a cube op, because it turns out to be the opposite of a cube category, is the monoidal category freely generated by an object, which is going to be like the interval or the one cube. And that's going to be acting like on C the way by this id, and then it has morphisms from the identity, the unit object. So this bold one here is the unit object, which maps to the interval, and then we have these projections from the interval back to the terminal object. Sorry, the unit object one, which satisfy this relation, and then we also have these symmetries. So to give a structure like this on a category is the same as to give a monoidal functor from this cube op into the endofunctor category of C. So this interval object maps to this ID functor, and then sort of tensor products, I tensor I maps to ID compose ID, and so this symmetry maps to this symmetry, and these maps map to these transformations, and so on. And if I uncurry this monoidal functor, then what that gives me is an action of this cube category on my category C. So the structure that we need in order to model identity types comes from an action of this cube category here. This cube category turns out to be, in fact, a semi-Cartesian monoidal category. So that means it's a symmetric monoidal category, and its unit object is a terminal object. I guess over here in cube op, the unit is an initial object, and so now if I reverse it, I get it's a terminal object. So that means it has projections, but it doesn't have diagonals. So we haven't introduced any diagonals on squares in our syntax. So it makes sense that we don't have those, but we do have symmetries. So this is sometimes called the semi-Cartesian cube category, or the substructural cube category, or the symmetric cube category, or sometimes maybe the affine cube category. And it was used by a bunch of other people. For internal parametricity, there was sort of a unary version of this which was used, and then the original BCH cubical model used this notion of cubical set, and more recently it's been used to add parametricity to cubical type theory and so on. So it has a long pedigree here, this cube category that we're using. The structure that we need is an action of this cube category here, but it's natural to formulate that also in terms of enrichment, because this thing here is a monoidal category, so its presheaf category gets what's called a deconvolution monoidal structure. And so if you don't know what this notation for coends over here means, then don't worry about it. We're not going to use that very much. This is the definition of this monoidal structure. For those people who know what it is, this is what it is. And then we have these representable objects, which I'm going to consider to be the n-dimensional cubes, which live in sort of this presheaf category, cube hat. And then it turns out that to give an action of this cube op on a category C is the same as to give an enrichment of this category C over this deconvolution presheaf category, which has powers or cotensors by these representable objects. So and those cotensors, those powers, are in fact these actions of the elements, the objects of this cube category here. Sorry, maybe I didn't say what this n was. This n is the n-fold tensor power of the interval. So the way we define this, right, this enrichment is that the n cubes in the mapping space are the maps in C into this action, into this cotensor by the n cubes, and then here's the universal property of these powers. So I claim that this means that the natural home for semantics of this theory is categories that are enriched over this semi-Cartesian cubical sets category. And in particular, this category itself is enriched over itself, but also any category of cubical objects in some other category E is enriched over this cube category with powers and copowers that are defined in this way using the similar sorts of coend constructions. So again, if you're familiar with this, that's great. And if you're not, don't worry about it. We won't really, we usually only use it in 1 or 2 places. So I want to say a little bit more about what this cube category looks like. Here's a description of it, which I find the most convenient to work with. So we're going to consider the objects of this category here. So this is not cube op, but it's opposite. Its objects are finite sets. Sort of up to isomorphism, you can think about a skeletal version where the objects are just the particular sets 0 up to n-1. But I like sort of the non-skeletal version where you take an arbitrary finite set. And then a morphism from one finite set M to another finite set N is a function in the opposite direction, whose codomain is not just M, but also M extended by a couple of extra base points. So the idea here is that this function phi says, given a dimension in N, it either comes from some dimension in M, or it sort of maps down to a boundary and sort of becomes a face map. And we require this map to be injective on the things that map to M. So more than one thing, more than one dimension can squash down to a boundary, but if it's not squashing down to a boundary, it can't get duplicated, and that's how we prevent there from being diagonals. And the monoidal structure is you take the disjoint union of these finite sets. So if we take a particular element of one of these finite sets, so here K is an element of our set N, then I get a coface and a codegeneracy map. So the face map sort of basically says I'm going to remove this element of that finite set and get a set with one fewer element, and then include it in oh, sorry, not the inclusion is the codegeneracy, because this maps go in the other direction. So if I include this subset into N, that gives me the degeneracy in the other direction. And then to get the face map, I have to map N to this subset of it. So I act as the identity on this subset. And then I take this one extra element K in N, and I send it either to plus or minus. And that gives me the 2 face maps that are in one direction. So this is sort of why I like to think about the non-skeletal version, because I can just say this here is some other finite set. I don't have to sort of worry about renumbering things. I just take away some element of my set N and I get another finite set. An endomorphism of a finite set here is just a symmetric group. It's just an arbitrary bijection from the set to itself. This is not a Cartesian monoidal category. Even though, so you might think, well, it's sort of almost Cartesian monoidal, because the monoidal structure is disjoint union, which is a coproduct of finite sets, and the functions go backwards. So it's sort of like the opposite of something whose monoidal structure is disjoint union. These plus and minus don't screw with that, but what messes up is this injectivity requirement. So if this were actually a Cartesian product, then a map in the cube category from N into K plus L would just be a map into K and a map into L, but that wouldn't necessarily be injective. But what we can say instead is that a map into K plus L is a map into K together with a map into L whose domain has the image of K removed from it. And that sort of ensures that this injectivity requirement is maintained. And so this is now not just an ordinary Cartesian product, but sort of a dependent sum of a function of this sort, and then a function of this, whose domain depends on what this phi is. So this is not quite Cartesian, but in some ways this is actually even better. So we can do a calculation here using this coend calculus, and I'm going to go through this pretty quickly. If you're not familiar with coend calculus, then don't worry about it. But the idea is what happens when we do a copower or a tensor by a representable object. So the general formula for a tensor or a copower here is this sort of day convolution formula. And so I'm going to plug in the representable here with this. So this is just a Hom set. And now let's what's going on here. So this I'm doing a coend over K. Now here I have this the coordinate lemma combines these two things here. So this is the density formula, I sometimes called it. And so now that just sort of gets rid of the K. No, sorry, it gets rid of the L. Sorry, what am I doing here? Oh no, sorry, it's not this one. It's over here. All right, so the density formula here matches up this K with this K and gets rid of that coend. And now this K here becomes that M. And so now I have this coend here. And now I have a map into one of these plus here. And so I use this sigma here. So I read it out as a sigma of this and this. Now this piece here, this phi that maps from n to m, doesn't depend on L. So I can put that out in front of the coend. And now over here, I have something that, again, I can use the density formula, the Koyanay dilemma. This L over here is all by itself, and then I have XL. And so I collapse those, and now I just have X of n minus P of m. So in other words, the n cubes in a copower by a representable don't actually involve any quotienting. It's actually just a coproduct of a bunch of copies of the n cubes, of the k cubes for different dimensions in X. And particularly interesting is the case of the cylinder. So this is the copower by the 1 cube. And so in that case, what we get is this is a coproduct of maps in the cube category from n to 1 of X of n minus the image of 1. Right, so what does it mean to have a function here from n to 1? So this is, or a map from n to 1 in the cube category is a function in the other direction from a 1-element set to n together with these 2 endpoints plus and minus. So there are 2 possibilities. It could be either picking out that this 1 element could either go into n, or it could go to plus or minus. So if it goes to n, then when we remove that element from n, we get something of 1 dimension lower. And so now we're talking about some lower dimensional thing in X. So we get a bunch of copies of X of 1 dimension, the n minus 1 cubes in X. And so but I've written this in a non-skeletal way. Or if it goes to plus or minus, then there's nothing to subtract. And so we just get 2 copies of the n cubes in X. So what that means is that if I'm looking at the cylinder, cube 1 times X, then, and I want an n cube in the cylinder, then it's either it's an n cube in 1 copy of X, or an n cube in the other copy of X, or it's an n minus 1 cube that's stretched out along the cylinder. So I think of this cylinder here as having 1 copy of X over here, and then another copy of X over here. And then the cylinder is supposed to go sort of a stretch from one to the other one. And if I want an n cube, let's say I'm interested in a square in here, so that the 2 cubes in here, there could be either a square that's entirely in one side, or it could be a square that's entirely in the other side. And so this is sort of a square here. This is in X2, a square in X. Or I could take a line, a 1 cube in X here, and sort of stretch it out along the cylinder to make a 2 cube in the cylinder. And like this boundary here, this is a 1 cube in the cylinder, which comes from a point in X. So we have a very explicit description of the cylinder here, cylinder on a cubical set or a cubical object X, without any quotienting or coends or anything like that, just in terms of the cubes in X. And I don't think that there's really nearly no other cube category for which you have a nice expression like this, as far as I know. It really depends very precisely on this having symmetries, but not on diagonals.
A quick check from Emily. It's the automorphisms of N, which are the symmetric group, right?
Mm-hmm. The automorphisms of N are the symmetric group in the cube category. And so in particular, the symmetric group on N acts on this set here, and it acts separately on these pieces. And then it acts on here by permuting them with each other, and then acting on each of them via an embedded copy of the n-1 symmetric group. Okay. All right. So I'm running a little bit long, so I think I won't have time to do this whole calculation that I wanted to do. But I want to say a little bit about how this this nice formula here for these cylinders allows us to model the type theory that we've got, in particular, our computation rules for the identity types. So in order to actually model our this type theory, and we need a bunch of stuff. We need coherence theorems to sort of make everything strict. We need transport and lifting sort of to make things, to consider sort of fibrant cubical sets or concubical sets or cubical objects. But we also, we'll talk more about those next time, but we also need these computation rules for the identity type. So these things like id of a product is a product of ids, id of a function is this function extensionality thing. And it's a little bit tempting to think that at least in cubical sets, we could sort of just define these id things to be whatever we want them to be, but it's not really that simple. The reason is, well, so the identity types here, we introduced this cubical structure because we wanted to model the identity type structure that we see. And so once we have the cubical enrichment, then to be consistent, the identity types actually have to be defined as this power, cubical power, by the delta one, cube one, sorry. So that's not something that we can define by hand. What we get to define is this cubical set X. So we get to define the individual sets of n cubes in X, but it's not completely obvious how that leads to a characterization of the entire cubical set of this thing here. There is a nice formula for this thing. It's just given by shifting dimensions, but that doesn't necessarily translate to a characterization of that whole thing in terms of categorical operations in the category of cubical sets or cubical objects like pi types and so on. Furthermore, for particular examples like A cross B or A arrows B or whatever, where we want to compute the identity types, we don't actually get to choose all of the types of the sets of n cubes separately because we have a categorical construction of these things. This has to be a product in the category. This has to be an exponential in the category. The pi types have to be this right adjoint to pullback in the category. So we don't really get any choice at all. They're determined by their universal properties. So to have these computation rules for id of AB or id of an arrow or so on, we really have to prove non-trivial theorems about cubical sets, or more generally about cubical objects. And this property of this nice property of the cylinders in cubicals in our semi-Cartesian cubical sets is actually what lets us prove these theorems. Let me yeah, so here I'll give the example of products, and then I'll postpone anything else till next time. So the products are pretty easy to prove because this exponential, or sorry, this power operation is a right adjoint. It has some universal property on the right, and so it preserves categorical products. So what that means is that the power here, the cubical power into A cross B, is the same as the power into A cross the power into B. And then similarly, if I sort of put that over a rearranging of the product, what that tells us is that we have this rule for identity types of product types, right? So the identity type of a type A here is represented by this power, but together with its projection to A cross A. So, right, so the fibers of this map here are the identity types essentially, because this is supposed to depend on two copies of A in the context, which is this thing down here. So what I need to understand id of A cross B is to look at this guy here living over two copies of A cross B. But I'm saying this thing here is isomorphic to the power of A cross the power of B, which then live over two copies of A and two copies of B. So that essentially the fibers of this guy are id A, fibers of this guy are id B, and so therefore the fibers of this guy, which are A cross B, are isomorphic to the product of these guys. So in our syntax, we actually had a definitional isomorphism here, sorry, definitional equality here. Right now here, what we just have is an isomorphism in the syntax, but hopefully we can have a coherence theorem, which will improve that. I'll say something about that next time. Okay, so here we didn't really use these special properties of the semi-Cartesian cube category, but when we come to talk about function types and the identity types of the universe, then we will in fact need to use that special property of the cube category. So we'll get to that next time. For now, I will just stop here. Thank you.
Thank you very much, Mike. So the floor is open for questions. Just send your question to Steve, and Steve is either going to ask the question or give you a unmute.
Okay, I have some questions here. So first is, I believe, a comment from Andy Pitts. It says, I recommend the nominal perspective. I would, wouldn't I? I guess that's the question part. And then he gives us a link to a paper which I don't know if it went to everyone. I can try to forward the link to everyone in the chat. Let's see if that works. Mike, I think there is a question in there somewhere though, which is whether you know how or if your approach is related to the nominal approach.
So depending on what that means, I think maybe I don't know the answer.
Okay.
So the standard, the cubical type theories, which are based on an interval variable, I think of those as being related to a sort of a nominal approach where the interval variables are sort of names that you can think of moving around. So that's not what we're trying to do here. We're trying to get away from having interval variables, but I don't know exactly what this is linked to, so I'm not sure if that's what he has in mind.
Okay, well, there, I sent the link again without a comment. I think that one. Yeah, it's just a comment. It's not.
Yeah.
The nominal presentation, Andy knows, and some other people know, is closely related to the BCH model of cubical type theory. I think there's a theorem in there, not just an analogy, but an actual theorem that relates to them. And that was proven, I think, by Andy way back in the beginning of cubical type theory. So there's probably some deeper connection there to your approach too. But let's move on.
So this paper that he links to is talking about a particular model, or talking about presenting this cubical set model where you're thinking of these intervals as names, and the paths are name abstraction. So it feels to me like that's sort of a way of thinking about the traditional cubical sets where you have interval variables thinking of them as names, which is a little different from the way we're trying to do it. But semantically, it's the same category of cubical sets. So when you're working just in a semantic world of sort of trying to build the model, then you might find that way of thinking convenient. I'm a homotopy theorist, so I find a homotopy theoretic way of thinking more convenient.
Okay, here's another question. This one's from David Jazz. Have you thought of defining function types out of a telescope rather than a single type in order to cut down on the nested pies?
That's a possibility. I kind of prefer to think of the telescopes as sort of meta syntax, and sort of I would prefer that the actual user of the type theory not have to think about telescopes, and so I find it more preferable to say that, say, the id of a pi type is just a triple pi, so that they don't have to think about what it would mean, like pi over a telescope or whatever. But that's definitely something you could do.
Here's a comment from Andy. Let's see. Oh, this is a question now. It seems like HoTT has very many definitional equalities. Is there any hope that by a careful choice of concrete syntax, some of them will disappear, become true because of the syntax? Question mark. I think we stumped him.
Yeah, I can't, nothing immediately comes to mind of how you could do something like that. But
Okay.
It's not impossible.
Here's a question from Emily, maybe an impertinent one. Can we see some of the other slides? Or do you want to save those for next week? Or do you want to, you'll
sure.
online, or?
I mean, I can.
Let's see the further questions before you start going through other slides, okay?
Okay. Sure.
Well, that's a call for the chair, actually. I'm just the.
Yeah, let's do other questions for now first, and then.
So here's a question, just out of curiosity, what happens if you remove the convolution condition on sim?
The involution of being a self-inverse?
I'm just reading what it says.
Yeah.
Probably.
Actually, I guess I don't know. It might mean one of the others.
Could be.
Yeah. So
Oh, involution.
involution.
Yeah.
What happens if you remove it?
Yeah, that's weird.
So I don't have an example where of showing where that would maybe break canonicity or anything like that. I guess it's because the sort of the only syntax, so the only semantics where I understand how to model the rules that the other rules that we're interested in involves these symmetries, which do satisfy that rule. I feel like we need that rule in order to be able to glue with this syntax in order to give a categorical proof of canonicity or normalization. That doesn't necessarily might mean that there might not be some more ad hoc syntactic way to get a theory with that computes without that rule. But in some sense, that rule is it's in any concrete type A, it's going to hold by definition of sim A, right? So sim of a product type is swapping the it's sort of sim on the two pieces, and so as soon as those two pieces are involutions, then sim on the product will also be an involution. So on any closed type, sim is already going to be an involution, and then you sort of really the only content that we're asserting is that it's also an involution on type variables, on unknown types. And in some sense, it might as well be there. And the same with the other of those rules for symmetry.
Okay. I have a lengthy question here from Jason Gross, a follow-up on the adding intuition for the symmetry. I think it's 3 steps. I'll start going through them and we'll see what happens. 1, if we were able to get J computation without sim, would that be enough to derive sim? And if not, I guess this is still part of 1. Well, I won't say that if not until you tell me the answer to that.
If we were able to get J computation without sim, I suspect that you would then be able to define a sim operation, but it wouldn't satisfy all the same equalities. It wouldn't necessarily be an involution. Okay,
then I can read the condition. If not, can we factor out the parts of sim needed for J computation from the extra parts? I'm not sure what that means. Here's 2. Or do you want to take that too?
Yeah, and so maybe I should say something about the J computation, right? So the thing that you sort of seem to need for J computation is the other Horn fillers. So you have so J, you have C, which is sort of given X and Y, and U, and then you sort of you have when you get this equality identity in the or maybe I'll say Y. A Y, so you've fixed some A and some maybe B and P, and then sort of you say A refl is equal to BP in the sigma type, and then you want to transport in this across this. So so if you want, if it's like this is E sub BP, then to get J computation, you want to say that if I do this thing for A refl, then that's an equality between A refl and A refl, and so then that should be equal to refl of A refl. Right. And then, so what this is, there's sort of the Horn filling goes on here. So this is because this is you're identifying, so this the second component here, you're saying here you have A, referral A, and A, B, P, I think. Is that right? Yeah, so this is referral here. Okay, so if you need to be able to fill this here, this cube, this square, because that's going to be an id depending on. So if this is a q here, this is going to be an id depending on q in id a from referral to p. And so this square here is that, which is going to be the second component of this identification in this in a sigma type. And then q is going to be the first component of that. A is equal to p to b. So you need to be able to sort of, so you're basically saying like e and referral are sort of two different fillers for this up to down to up square, and then you need to be able to identify them with each other. So that sort of comes if you have this sort of unique transport in the opposite direction. So I mean, you could directly assert top to bottom fillers, but I suppose if you wanted to sort of get that without having symmetry, so that might be a possibility.
Okay, thanks for that.
Yeah.
Detailed answer. I'm going to push on here.
Yeah, sorry.
No, that's okay. Jason, I'm going to skip your second question. You can put that in the zulip, and I'll jump to the third one in the interest of saving time. The third one is there an intuition for why sim is enough for canonicity, and why we should or shouldn't expect that it's both necessary and minimal on top of everything else we already have for getting strong normalization or canonicity?
So my intuition for why it should be sufficient for canonicity is the semantics. So because once you have sim, then you have a global sections functor from syntax to semi-Cartesian cubical sets. And semi-Cartesian cubical sets seem to have all the structure that we need in order to build a model of the theory. I haven't talked yet about how we use that structure specifically to model like id of a function type and id of the universe and so on. But once we do that, then we'll have a model of the theory, and we can do a gluing argument with that global sections functor to get a categorical canonicity proof. So that's my intuition for why symmetry is exactly what we need for canonicity.
That's a good answer. Thank you. Okay, I'm going to push on then. There's some other questions here. From David Jazz again, do you have an inkling that a similar approach could work for a directed type theory where we have map of AB, which has a definitional directed univalence, such that map of AB is A arrows B when A and B are types?
Right. So it's very tempting to think that this might be true. To my mind, the obvious thing to do would be to just get rid of this piece, and then instead of one-to-one correspondences, that you talk about sort of functional correspondences, which are sort of only contractible on one side. It might be possible to write down a theory like this, and it might be possible to build a categorical version of it. And I haven't thought very much about it because it's not clear to me that it's the sort of directed theory that I would be interested in, because when you sort of what this would give you is sort of directed transport from left to right all the time, and in particular you're going to have directed transport from left to right in HOM types, and so you're going to have a composite of some situation that looks like this, which so I don't expect to be able to compose backwards with an arrow like this in a category. So you need some. In order to get some sort of more categorical notion of composition, you need some additional restriction, and I don't know what that might be.
Okay. All right. We seem to have exhausted the chat. I'll take a question then, if I may.
Go ahead.
There seems to be a connection here with the equivariant cubical model. where we also have those, we throw those sim operations in to the cubical model. So, and that's what apparently what it takes to get the resulting model category to be equivalent to spaces. So there seems to be some sort of a nice connection there. I don't know if you have anything to say about that. It's more of a comment, I guess, than a question.
Yeah, so the equivariant cubical model is about, I mean, so you're not changing the cube category, right? You're starting with the Cartesian cubes, which do have symmetry, but then the point is that you have to use that symmetry in constructing the model structure in order to model classical homotopy theory, right?
Yeah, that's one approach. There's another approach where you actually do change the category. You put the symmetric groupoid also up in the exponent.
Yes, I remember that now. Right.
So you can do it that way too.
Yeah.
So,
yeah, the symmetries are sort of really intriguing, the role that they play. I don't have a general answer for that, I guess.
Right. Okay, just an observation.
Yeah.
It might come up when you start to do the gluing, when you look for your target.
Yeah, so it's a little bit subtle. Hopefully I'll have time to talk about this next time, but there's a bit of a disconnect between the cubical set model that seems like the natural one to glue with, and the cubical sets or cubical spaces that seem like the natural one to model homotopy theory with.
Right.
I think those may not be the same.
Okay. But you're going to end up gluing into something that has these symmetries, right?
Well, yeah, in the sense that we're working with cubical sets that have symmetries in them. We're not adding extra symmetries the way you were talking about with the symmetric groupoid.
Yep. Right. I see. Yep. Okay, so I think the chat is done.
Okay.
Let me suggest that we continue our discussion on the Zulip as we did last time. That was very successful. If anyone here is interested in joining the Zulip and is not already in there,